Yesterday we introduced colligative properties, and we said that one colligative property was boiling point elevation. What did you find out about the boiling point of the solution compared to the boiling point of the solvent? It is higher. When you add solute to solvent, the boiling point increases because it becomes more difficult to break intermolecular forces that have formed within the solution. As a result, you have to increase the temperature in order for the solution to boil. Today we're going to look at freezing point depression. What you're going to see with freezing point depression is the freezing point of the solution is going to be less than the freezing point of the solvent. And that's because when you add solute to solvent, what happens is it becomes more difficult to form intermolecular forces in order for the substance or solution now to freeze. So the freezing point of the solution gets depressed or lowered. You go about this type of analysis grossly similar to what we did last time. When you want to calculate the freezing point of the solution, you first calculate the change in freezing point, and the only difference here as compared to what we did the other day is you'll have the molal freezing point constant. We'll find that on the back of your periodic table in a minute, times the molality, which you know how to calculate, you were just assessed on the quiz, times I, the number of particles in solution that we talked about the other day. Solvents have unique molal freezing point constants, and those molal freezing point constants are found on the back of your periodic table on table 2. The solvents are listed here, and the molal freezing points in degrees Celsius, kilograms per mole are listed here. For example, acetic acid, a solvent, has a molal freezing point constant of 3.90 degrees Celsius, kilograms per mole. Cyclohexane has a molal freezing point constant of 20.0 degrees Celsius, kilograms per mole. Water has a molal freezing point constant of 1.853 degrees Celsius, kilograms per mole. So for freezing point depression, we'll need the molal freezing point constant, which is found in the last column. Yes?
Why does that cyclohexanol not have a boiling point?
Cyclohexanol doesn't have a boiling point or a KB listed. Perhaps the substance, well, the substance does boil, but perhaps it's too tedious to measure. The freezing point of the solvents are in this column here, and again, solvents have unique freezing points. Water freezes at 0 degrees Celsius, phenol at 40.90 degrees Celsius, nitrobenzene at 5.76 degrees Celsius. If you make a solution in which water is the solvent, will the freezing point of the solution be greater than or less than 0? Why will it be less than? Because the freezing point gets depressed, so it has to be less than 0. So the freezing point of the solution will be less than the freezing point of the solvent. Okay? To calculate it, you'll first calculate delta TF as shown here, and again, the only change is right there with KF. And then to calculate the freezing point of the solution, you will do so by using the freezing point of the solvent, and here's the major change. You will subtract the delta TF. Two key differences. The freezing point gets depressed, so you must subtract the delta TF that you calculated here. Everything else is grossly similar to what we talked about the other day. So let's walk through a problem. In your notes here, freezing point depression, as I said, when you add solute to solvent, the freezing point's going to be lower. That's because it becomes more difficult for those intermolecular forces to form between solution particles, if you will. You'll calculate it using both formulas as we illustrated already. In this first example, it says at what temperature will a sodium chromate solution freeze? That's what we're looking for. We're going to dissolve 103 grams of sodium chromate, that's our solute, and we're going to dissolve it in 100 grams of water. So let's take a look at how we approach this type of problem. It's grossly similar to what we did last time. In regard to our pertinent information, our formulas are there. We want to know the freezing point of the solution. That's what we're looking for. The mass of solute is 103 grams of sodium chromate, and the mass of solvent is going to be 800 grams of water. Questions on pulling the variables out? We're going to first solve for delta TF. We've got KF times molality times I. How do we find KF? Do we use the solute or solvent? Solvent. Our solvent's water. Our KF is 1.853 degrees Celsius kilogram per mole. How do we get the molality? Do we use the solute or solvent? First the solute. We're going to convert that to moles. And I don't know why, but some kids had this upside down on the quiz. Not necessarily in your class. So we'll get moles of that. We have 103 divided by 161.99, and that's 0.636 moles of solute. Is that my molality?
No.
No, I have to divide that by
0.8.
the kilograms of water, and I did see some poor conversions in the other class. Be very careful with your conversions. You have 0.795 moles per kilogram. That's the unit for molality, or you can write little m. How do we get I? Do we take the solute or the solvent?
Solute.
We take the solute and we write a dissociation reaction. We generate ions. Sodium's in group 1. What's its charge? Chromate is 2 minus. Now you need 2 sodium, 1 chromate ion. The value of I is 3. 2 plus 1, 3. So our delta TF is 4.42 degrees Celsius. And again, the only real difference there is you used KF. The next piece is a little bit different because to get the freezing point of the solution, we're going to do the freezing point of the solvent minus delta TF. So our solvent is water. Water freezes at 0 degrees Celsius, from which I will subtract my delta TF, and this solution freezes at negative 4.42 degrees Celsius.
You done messed up, AA wrong.
There's really not much difference here from what we did the other day. Calculate delta TF, calculate the TF of the solution by subtracting from the TF of the solvent. Here's a second example that you can give a try. Tomorrow we will either finish up the note packet or do a mini lab on solutions. Which formula? If you are calculating the freezing point of a solution, you will use the two formulas that I indicated initially. If you are calculating the boiling point of a solution, you'd be going after delta TB, and then you'd have to add the delta TB to the solvent boiling point. I can't hear her question, please. You have to find the change first.
Well, there goes that.